because I'm managing 1 year now into it's really different decision. Still everything which is
No, I don't know. No, it's okay. I just talk about statistics, which have my university contract. It's called data science, statistics for data science.
Il y a un tweet sur ça?
So can we start? Is it okay? Take enough food and drinks, and I would say that we start our session now.
Should I check the stream or
No.
no? Okay.
So, hello everyone, welcome and to the Papers We Love session. So this is the first time we try this, and as you can see we're also trying something else for the first time. I'm really excited about. So we see all our equipment here, so now the most meetups that we are going to stream them live on YouTube. So you can see the information about our channel in the meetup links, and yes, I will now, without any further delay, let Chris start with his presentation. So thank you.
Slideshow. Ready for start? Okay, hi, my name is Chris, and I'm going to talk about one paper that you might have read or not read. It's called Generative Adversarial Networks by Jan Goodfellow. So let's do a show of hands. Who knows what GANs are? Okay, who has read the paper or another paper about GANs? Okay, a number of people, but not everyone, that's good. GANs are pretty popular, and I picked the paper because of the impact it had, not necessarily because this paper is the actually best presentation of the material. So I'm trying to go a bit through the paper and a bit to contextualize what has happened since 2014, because 2014 is not that long ago, but if you look at the number of papers that have published since then that directly reference the paper, it's quite an explosion of papers and ideas, and not all of them are incremental. Some of them are fairly incremental, but there's a lot of interesting things in it. So what are GANs? I have the link of the paper so you can look at it yourself. But let's look at what GANs are just by looking at the title, and let's work through the components, generative adversarial networks. So networks is simple, right? I just Googled what is an image of a network, and I think everyone knows what a network is, roughly. And the next word is adversarial, right? And it is defined as involving two people or two sides who oppose each other. And that's also the definition we need to understand the title. So I'm just leave it at there for now. And the next thing is generative. And maybe there's something to say about it, because usually when we think about machine learning, it's often a supervised situation where we have labels, and also we are just interested in like classifying things or labeling things. So we just learn a discriminative model, such as support vector machines or decision trees, and they learn a decision boundary. So they learn how to tell apart the different samples, the different items in your class, and that can have different shapes. In 2D it's a line for support vector machines, and 3D becomes a plane, a hyperplane, and so on. And what they do is they model a conditional distribution that, given the data, they model the probability of the right label that you're interested in. And in generative models, it's kind of the opposite. So it models the probability of the data given the label, and then you can use Bayes' theorem, for example, to infer what label you should give to a new sample. A really simple case of that is naive Bayes as a classifier, where you can just calculate the probability of having a certain label by assuming that all the features are independent and just like using the product rule, and you get your probability that you look for. So Now we have all the components. We have networks. These are just neural networks. We have adversarial, so it's two things that oppose each other. And we have something generative. So we don't want to learn a discrimination boundary, but we want to learn how to generate or want to learn a distribution. And so now let's take two things together, generative and adversarial, and so let's have a generative adversarial situation. So in this thing you have two players. One player here is the police, another player is the counterfeiter, and he creates fake money. And that really quickly involves a feedback loop, right? Because he creates fake money, eventually people will notice that there's fake money, so they will catch him and he's like, oh, that's bad, I need to make better fake money. So there's a feedback loop. He creates a fake, or he doesn't use a fake, or maybe he uses both. The police or someone else eventually will figure out what's fake and what's not fake, and in this situation the counterfeiter will learn from the police what makes a good fake and a bad fake money piece, right? And now let's add the missing part from generative adversarial. We need networks or functions, because networks are just functions. So a general adversarial function in this thing is we have two players, the police and the counterfeiter, or a discriminator, which is the police, and a generator, which is the counterfeiter. And the police, or the discriminator, tries to discriminate between two things. And because we're in machine learning, we actually have just data, and data is drawn from some distribution, and that's what we're interested in. So we have some true data distribution, a set of images we care about, for example. And that's one thing that the discriminator tries to learn, and it tries to discriminate that from fake images or fake elements that I tell are from the same distribution as the true data, but they're actually not. And now we just pit them against each other and say, well, the generator needs to trick the discriminator to think that samples generated by the generator are actually from the true distribution. At the same time, the discriminator tries to do the opposite. He tries to identify which one is from the true distribution and which one is just generated. And now if we add networks instead of functions into it, it kind of looks like this. We have at the bottom right amnestic samples. So this amnest is just a data set with hand-drawn digits. In this case, they are the real data. And we have this generative model at the top that is trying to generate fake images that look like hand-drawn digits. And then we have the discriminative model below that takes either a fake image or a real image and has to decide and label it whether it's fake or not. And then we just train them by taking turns. And going a bit more into detail, what this looks like is essentially the differentiable function d, which is the network. If it gets an x that's actually from the data, it tries to output 1. It's essentially modeling a probability that the item it sees is from the actual data distribution. And on the other hand, if I give it a fake element that comes from a differentiable function g that I usually prime with some noise, so it just generates different things, but then it tries to output 0 as the probability of it being from the true distribution. And what's kind of interesting here is that because it's differentiable, I can use gradient descent, and because I have networks, I can do backpropagation and save some time over other optimization functions. And now I just need to write this down in terms of like loss function and in terms of like how does it actually interplay as a concept. And this is kind of the only formula I'm going to show. There are some proofs in the paper, but I think you can look at it yourself. It's not really complicated. What's important is that there are two terms to expectations. On the left one, where x is distributed like the real data, that's just the discriminator loss, right? And it tries to output 1, the discriminator. On the right part, the discriminator takes a sample that's generated by the adversary. The adversary tries to fool the discriminator and tries to make the discriminator output 1 in this term, whereas the discriminator tries to identify it and output 0. And well, then you just try to maximize the capabilities of the discriminator while you try to minimize this function with the generator by creating better examples. So that's what it does, right? And it kind of looks like this. If you look at it as a density estimation problem, you have your data distribution, the black dots. You have a model distribution, that is what the generator generates if you input random noise. And you see down there the set that's randomly sampled. And then you have a discriminator, the blue one, that tries to tell apart which samples are from the true distribution and which one are from the generator, the model distribution. And now we just switch between training and updating the discriminator and then training and updating the generator. And you kind of do this until it starts converging, right? So eventually you update D and it becomes a bit better at identifying which samples are fake and which one are not fake. And then you train the generator so it like moves the model distribution closer to the data distribution. And you keep doing that, and eventually you reach an equilibrium, hopefully, where the best thing the discriminator can do is just flip a coin and guess, because your samples look so realistic that it can't do anything else. And the same in a different type of image, where you see at the very top there's a 0 and a 0 with a dash through. It's the true data, and down below you see g of z, which has initially some really weird things. These are the generated distributions, and the dashed line is the decision boundary of the discriminator. Well, and then you train the generator so from the first image to the second image in the top line. First you try to make the discriminator better, right? So it tells apart which one is which. Then you iterate and you try to make the generator better, so it moves the samples across the decision boundary, and you go on and on and on, and eventually you hopefully reach an equilibrium, right? The question is like, does it work, right? You can easily come up with a scheme, but like the question is like, is it realistic? And as you might guess from the amount of papers published, it does work pretty well. These are some images taken from the original paper. Usually especially initially, they outputted really small images with really low dimensions, but now they can go up to, I don't know, 800 by 800 with no problems. So here you just see some different data sets, numbers, faces, animals. And the rightmost row, you see the image that's closest from the true data set to the one that is generated. So it's kind of an indication that that the model just didn't memorize and just copy things from the data set into the output, but actually output something that looks different. So that's good, and this was kind of a visual kind of hint that it works. And at that time when it was published, other generative models were about as good, or maybe better, maybe worse, but was a close call. And the second answer we can give is, well, it does converge in theory, so there's a proof in the paper which we can look up. The important takeaway maybe is that if you find the optimal solution, it's actually the minimum of a divergence between the distributions. So it's actually a fundamental statement about you really learn the distribution of your data. But while there is a problem with it, because that's only theoretical results, if you do stochastic gradient descent, then you have no guarantee of actually hitting it. And if you read closely, it says if D and G have enough capacity, so possibly infinite capacity, and also if you have potentially infinite time and samples to train, then you'll converge. But in practice, it might mean that you have no idea what's actually going to happen and how close you are. And yeah, I took that a bit away. So theoretically, we have this global optimum where you converge to the right distribution. You're guaranteed to converge if you have infinite data, infinite capacity, and if you do the training actually correctly, but you with stochastic gradient descent kind of don't know. So why do we still care, right? Why is there so many papers? And now I'm kind of leaving a bit the scope of the original paper, because conceptually you now know what GANs are and what you can do with them. I want to show why it's interesting also for data science application, not just for machine learning who say, oh, we can now do a better way of density approximation, which might not be relevant for the real world at all. One thing is it just seems to work pretty well. And it seems to work pretty well because it avoids problems of other approaches where you need to model some really complicated integrals that you actually can't quite approximate, or you have to do MCMC sampling and you don't know how many runs and it just takes forever. And another nice feature is in your loss, you never put a true sample from your actual data set into the generator. You only put the output of the discriminator into the generator. So you don't feed through true information, you only feed through the output of the discriminator. And that's a nice property, because you kind of are sure that you don't just have a one-to-one copy of your data, which might be a way to fool anyone into believing you've learned the true distribution, but you actually haven't. And the other thing is that unsupervised learning methods are incredibly useful, and in practice, when we think about all the machine learning papers and the great advances in deep learning, for example, they're often on a really clean, not really data science setting. You have a clean data set with labels, and you kind of start working on it. In practice, you have missing values, the data scheme is inconsistent, you run into a million problems, and then often you don't really have the labels, or unlike Amazon, you can't crowdsource labeling. Or you might not want to crowdsource because you work at a bank and you want labels for bank transactions from your customers, and you don't want to give them to Amazon Amtrak and like have strangers label them for you. So there's many reasons why one should care and also why we should care as data scientists. So let's just look at some examples, some extension of this work to kind of convince you that looking at this paper or knowing these techniques is interesting and maybe also something you could look at even if it's not as production ready as decision trees right now. One really cool paper is DiscoGAN, or there's also CycleGAN, and it extends the GAN framework a bit, but what you do is you essentially train two GANs on different data sets that can be completely unrelated. And you don't need any correspondence between the two data sets. They can be completely unsorted and random. And then it learns how to transfer certain things. So in this example, you input a handbag, and it outputs a shoe that fits the handbag. But you don't need training examples where you say, this is a handbag and this is a matching shoe or vice versa. It just infers that essentially magically, automatically. And well, that's interesting, and what you also can do is you can use it to learn representations. So once you have trained a generator and once you have trained a discriminator, they might encode information in a compact way that you can actually use. And there's a representation learning paper that does something that you might know from Word2Vec, where you actually learn a representation that you can manipulate and navigate. So here they can actually turn the angle from which you view a face without actually having to input like a sequence of faces that are seen from all angles. So it learns how to kind of transfer from different faces what it means to be viewed from a different angle. And there's another application here where they have images and they look at their representations, and you can actually kind of start doing arithmetic on it. So if you have a man with glasses and you subtract man, then what's left is glasses, and if you add woman back to it, you get pictures with like women in glasses. They don't all look really perfect, but it's also like fairly initial work, and for some applications people have gone pretty far with it. There's GAN for creating fashion, and what they do is they train it on models and they train it on well, clothing, right? So in this case it's dresses, and there are actually no models, no like human models where they do makeup and take photos. They just output these photos, and some of these photos are real humans and some of them are not. Like, can you guess which one is a real human and which one is not? Because so the third one in the first row and the last one in the bottom row are the only real photos of people there. The rest is completely generated by computers. That's, I think, pretty impressive. And there are some other things that people do. There's image-to-image translation where you input a sketch of something and you fill it out with like something realistic. So in this case they had handbags and they got a sketch from the handbag and tried to refill it out. There are sort of applications in the image area. But, and that's also interesting, maybe because not everyone, especially in Luxembourg, works on images. It's just that the images are usually the easiest thing to work with because they're continuous. And if you need to do gradient descent and continuous, like little improvements on an image, it's really easy to add a little bit to an image. It's really tricky to add a little bit to a categorical variable or a word, for example. So there are other examples too. There's Passcan, which I think is really cool, and especially because we're at a security institute, it's cool. So they take leaked passwords, which we have plenty, right? And then they want to kind of accelerate like dictionary attacks on it. So they train again to generate passwords that look fairly much like passwords that have leaked already. And it discovers structures in it that people do by replacing certain letters with certain characters or vice versa, or concatenating certain elements. So it actually helps you to extrapolate a brute force attack based on real password samples, and it works surprisingly well, which is already a bit creepy. What's even more creepy is this one. It's called Malgan, and they take malware, and they take a malware detector, which can be any virus scanner they can buy for really little money, or any intrusion detection system that might be a bit more expensive. And that will give them, given some sample, will give them a 0-1 output, right? I detect this as malware, or I don't detect this as malware. And they came up with a scheme to use this 0-1 output to also train a malware generator that can essentially avoid detection for a given generator. So whenever there's an update of a virus scanner, I just run this scan for a bit and I have malware that's undetectable again. And I can do that like as soon as they push it to the cloud, which is pretty creepy, and they published everything, like the code is there. It's quite interesting, and of course also quite controversial to think, should you publish something like that? But they argued it's better that everyone knows and everyone can do it rather than if just the bad guys figure out how to do it. And well, there's a long list of tasks in data science where you want to use where you're in an unsupervised setting like this, and where you want to extract features for presentations, rather than relying on labels, because as I said, we might not have them, they're missing values, the data is confidential. Often there are relationships between samples that we are not aware of, or that we want to automate, like in the example where you have shoes and handbags, but they don't have to be shoes and handbags. They could be anything. You could relate fridges and frogs, and I don't know what the output would be, but if there's a relationship between these things, well, it will come up with a good guess. That might be very interesting to see. And then often, using data is often only a means to an end, because you want to simulate something or train a reinforcement policy or something like that. And we can train again completely unsupervised by just fitting in the data we have, and it comes up with realistic data we can use to run simulations from. So, are there any problems with it? And obviously, otherwise we wouldn't be here, right? There's a big problem in how to train scans correctly. They're extremely unstable, and whoever has tried to train a GAN knows how painful it is to actually do it. And there are a lot of problems that are kind of systemic that happen, so you often have to train more than once to make sure that you don't run into one of these problems. And there are a million papers, well, not quite, but there are a lot of papers that propose a better way to train GANs, by using a different type of loss or a different type of bootstrapping or whatever. There's also a paper that says that all of them are pretty questionable, because whenever someone publishes a paper with a better strategy to train them, they often also have more computational power, so it's not quite clear if it comes from the additional computational power or if they actually come up with a better way to train them. So in this, because it's so young, there is no good test to actually do that. And the other thing is, well, how do you know that your GAN actually makes sense? With images, it's pretty easy. If you look at a person that has like 4 eyes or 2 heads or 5 hands, 6 fingers, we know this is not quite realistic. But if you output something else, like passwords or maybe fake bank transactions or some other, if we ask for relationships between fridges and frogs, we have no way of actually verifying what that means. And we do have some idea how to, for example, if we only care about the distribution, so we want our GAN to generate samples that match the input distribution as much as possible. We have ways to measuring and estimating that. But people can show that these measures, because they only talk about distributions, often don't capture what people actually care about. So when people evaluate GANs that output pictures, images, they don't usually look at the loss or the distribution, the difference in the distribution. They use a pre-trained net like ImageNet that does image classification, and they look at the classification performance on fake images generated by the GAN rather than looking at the distribution, because that actually captures what we care about, namely that the images look like something we expect, rather than that the distribution is super close but we still have 3 eyes. Right? So often you end up in a situation where you don't quite know how to evaluate this correctly, and you maybe need to accept that you don't quite know, but if it works for you, it works. Also makes a lot of results really hard to compare. And with that, I'm actually done. So in summary, right, adversarial networks do indeed have 2 networks that play a game against each other, trying to generate fake images that look as real as possible. Because everything's differentiable, we can train it with standard neural network methods. And it outputs pretty decent results, but the research isn't done yet. So with that, you can go to Jan Goodfellow's site. I stole a lot of images from him. He has a lot of slides online. They're really good. There are often also videos from his tutorials that he gave. So if you want to know more and more in depth also about the mathematics, then watch one of his talks. Otherwise, I'm done. Thank you. Okay. Has anyone questions?
Yeah, I'm very curious and more use cases. Do we have some other use cases, just to have fake of money, or for example, fake of signs on the street or something? Like
so based on what these image-to-image translations do, there's a lot of things where you have a certain view on your data input, and you have a different view on your input you want to transfer between these two. That can be not image-to-image, but also text-to-text translation, for example. There's work where you have 2 languages and you want to translate, but you don't have a correspondence between the 2 language text, right? Something like that you can think about. Then there are GANs that output essentially things that feed into a simulator. So you train a GAN on maybe generating labyrinths, for example. You have a bunch of labyrinths. You want to train more because you want to train your reinforcement algorithm to find the path really quickly. So you want more of them, so you train them, and you can use the GAN to actually have an on-the-fly generator for more things. There are also just text generators. They are conditional GANs where you actually can prime them with certain things, so you end up more in a situation like these here, where you say, well, I have this type of clothing, what would fit through it, and then you can generate something like that. This is applications I've seen. There are applications for video where you predict what the next frames would be, which seem to be working really well.
Have you seen something on voice generation? I think it's a startup that made something like this, but I didn't find no.
I haven't seen anything, so I know that there's WaveNet, but they don't use GANs right there. And that's
No, it's something so very, very strange, because you can use this, it's very good, but on the other side there's no information, behind.
Yeah. No, I'm not aware of any GANs that directly output voice, but there probably is someone that submitted something to iClear, and I just haven't found it yet. But in theory it should work, right? And there are some advantages with GANs. You can sample faster than from WaveNet, where the generation is super slow. Yeah. Okay. Any other questions?
I'm just wondering, does it need any kind of overfit protection or protecting the
Yeah, so if you...
I may, Chris, before answering, could you repeat the question so we can add...
Oh yeah, so the question is if you need to protect against overfitting, right? And
it seems to me that the best, the kind of the global minimum of this function will be if this generator manages just to learn all possible examples and output each one at random. But I guess
well, yeah, usually you have a continuous infinite distribution, right, where you say I can't have all of them, because if you have all of them, things become a lot easier, right? What you need to be careful though is that the relative powers, if you have a generator that's already very perfect, it will always fool the discriminator, so the discriminator doesn't really have anything to learn from, and vice versa. If your discriminator just detects everything the generator does, it will also be stuck in the situation where it can't improve because it's not good enough to get any information through. So besides overfitting, what you really need to be careful is that both models are kind of on an even ground, otherwise you will not train effectively and you'll just get stuck in a really bad situation. If you completely overfit, I'm not quite sure what that would mean. If you have because you're trying to learn the distribution, right? So if you have a representative example of the distribution, it's probably pretty good. The question is how much generalization do you need to find the distribution where you draw your samples from?
Yeah, well, actually, yeah, this is kind of the main question. That you need to push at least one of these to learn some generalization, not just memorize.
Yeah, so memorizing is not that big of a problem because you never input a real sample in the generator.
Yeah, this was my guess why there was this last point in the positives in the pros.
Yeah, so here you see on the right, the generator generates something that gets into the discriminator and that gets into the loss, right? Yeah. It makes it a bit easier, I think, to not overfit.
Okay.
Okay. Any other questions, or should I hand out to the next speaker? Good. Yeah. So I'll hand over to Eric.
Oh, I see my sight is not that good anymore. Okay, so who is a little like me working on the edge of machine learning and data management in this group? Huh? A few people, I would say. Okay, then I guess you're going to be really interested by this paper. In just 1 second. So. How do I go on full screen?
Last option.
Last option, okay. Thank you. Okay, so the paper I choose is called The Case of Learned Index Structures. This is a paper from 2017 written by Tim Kruska, and it's a joint work between the MIT and mainly Google. Right? So for your convenience, you can scan this QR code and you're going to land on the page to download the paper. Now, First, I'm going to make a small review and talk a little bit about data structures or index structures in general, so that you know what basically they achieved in the paper with the machine learning algorithms. So why does anyone want to learn index structures and how they actually achieve it, and then I'm going to conclude. All right, so this is a good old hard drive. On the A symbol, this is called a track. The B, this is a geometrical sector. C is a sector. And now D, this is a couple of adjacent sectors. This is called a block, right? So the block is the unit that is going to be read by the operating system. Now once this block is in main memory, it becomes a page. So this is basically a virtual block of fixed size. In one page there can be several blocks, or just or the other way around. So it's not necessary that one page is equals to one block. So this is important because those index structures, they're optimized to play around with those two chunks of data. Okay, so now one major index structure is the so-called B tree. So this is basically a balanced tree. That means that the height is the same for all nodes. So we're always taking the same. We always make the same path lengths to get to the leave nodes. You insert data there. It corresponds to key value pairs. Now this comes with two flavors. So the key is the so-called search key, not necessarily the primary key, but the key you want to use to index your data. So this can be a timestamp, it can be anything else. And if you are indexing with the primary key, then basically you save the data right behind the key. So it means it's exactly adjacent, so that means the one would have the key and then just the value behind it. Now if you use it as a secondary index, there you're going to save the key, and behind the key you're going to find basically the address where you're going to find this data tuple, this data row in your block or your page. All right. Also, usually the nodes of such a B tree, they are equal to one page size, so that they can always read one sequential amount of data from the disk. All right, so they are particularly good for range queries, okay, because you see this is sorted, and basically it's pointing to some sorted data on the disk. An example of a range query is just we select the product name and unit price, where the unit price is between 18 and 19, right? So this type of data structure is used in InnoDB, which is the storage engine for MySQL. So not exclusively, but maybe this is the most prominent example now. Another indexing structure is the hash table. So I guess you're pretty much familiar with this one. So it's an array structure, and as an input it takes some value. So here it's a string, it's the first name and the last name. And with a hash function, this is going to be mapped to some index in the array. And this is a very good data structure if you want to perform point queries, such as give me the first and last name from the employees, where the employee ID is equal to 18. So there we have a 01 access time. Okay. This, for example, is used in PostgreSQL. Again, not exclusively, but it's a famous example. Now, the last data structure I want to introduce, and they also use in the paper, it's the Bloom filter. So this is a probabilistic structure. It maps a set of data, or a sequence of data, data characters or symbols, to a bitmap. And with this, you can ask, is this key in this set or not? So the Bloom filter is a bit particular because it returns false positives, but it never returns false negatives. Now, what's very interesting with this data structure is that it has a small storage footprint. So sometimes if you just want to know if the data is in the set or not, you can rely on this because it doesn't take a lot of additional space. So you might wonder where this is used. So as an example, this is one type of storage structure you use in databases. So it's a so-called LSM tree for log structured merge tree. So we see different levels of data, and each of those data chunks, those are files containing certain keys, okay? But not all the keys from your key space. So if you're searching for a specific one, you can, with multiple threads, look at different files, and here quickly ask the Bloom filter: is my key in this file? Yes or no. So is it in the file? It can say maybe, or it can say no. Okay, but this false positive rate, it can be tuned. Okay, so you can specify to what degree errors you can have. Yes, please.
So basically, if you use hash functions.
Yes.
And so if you use hash function which have very huge output space.
Yes.
You end up in the case you shown before.
You mean
for key value storage in PostgreSQL?
It's not really. It's not the same type of hash functions. So basically, here you're trying to run it to different hash functions, and it's going to be hashed to a bitmap. So actually, here with an array with different indexes, and you're just going to set a certain flag. So for example, here the X would set the array position 1, then I don't count, but you see the blue ones. Okay. So for example, if those bits are set, that means that X is in the set. Does this answer you? So it means not one key is not going to be mapped to one bucket, but more to a combination of buckets.
Okay.
And you're going to look at which flags are set to determine if your key. Now, if you increase the size of the bitmap, the lower your error rate is going to become. But then on the other hand, you're going to lose space. Yeah. Okay, this example, so those log structured merge trees, they are used in Cassandra, RocksDB, and LevelDB. So this is basically how they store their data. All right, so now the question, why would someone want to learn those index structures? So, I mean, after they have been optimized for decades, basically, since the beginning of databases, they start to optimize index structures, to have better access patterns, to improve some workloads, right? Now, I thought one reason could be that you can personalize the workloads more easily. So, for example, you take a B tree. This is very good for range queries, right? So if you think it has been optimized for decades for those range queries, maybe with machine learning it's going to be easier to learn data structures for personalized workloads. And this reason basically leads me to the other one. So hardware is changing, right? So I showed you the example of the hard drive, but now we are already at SSDs, and how the data is managed is totally different. So it's likely, or it can be, I'm not going to make such a very bold statement, but it can be that data structures that have been optimized for decades, they become obsolete at a certain time, okay, when the hardware changes. Maybe if we can learn those index structures with machine learning, it becomes easier to come up with new ones. And finally, hardware evolves. So in the paper, they learned the index structures using normal CPU. But if you think of GPUs or FPGAs or TPUs, which are tensor processing units for TensorFlow frameworks, for example, if you think of this type of hardwares, maybe those learned index structures, they become much, much faster. Okay, so let's look into how they learn those index structures. So the B tree maps the lookup key to a position in a sorted array. So you remember when I talked about pages and blocks? So one optimization that is often used is that you just index the first key that you can find in the page. So you can be sure on the left side, you know that for another key, it is going to be at the position plus page size. So you can just seek through page size to find your actual key. So it's sufficient to store basically just the first key of the page. Now, if you think of this from a machine learning perspective, the model would be the following. The keys are the features, and the positions, they are the labels that we want to have. So this is basically illustrated now on the right side, where we don't have this type of tree structure, but we're going to predict a position. So we're not doing lookups anymore, we're doing predictions, right? So, but here, when we're going to do this, we are going to have error boundaries. Basically, in our predictions, we're going to have a min error and a max error boundary. And this is very important because usually in machine learning, you're going to try to minimize the average error rate. But here, what you want to do is basically make that interval of position minus the min error and the position plus max error. You want to minimize this this interval, basically, right? Now, in the first naive attempt for data sets of 1 million records, so I give you just a few numbers, but it's going to be in much more details also with the cost function and everything in the paper. So with fully connected neural networks of 32 neurons per layer, they managed to average 1,250 predictions and lookup per second. This is quite good. Yet the B tree is still 2 to 3 times faster. So now, what happened? So, firstly, the B tree is a highly optimized data structure. Now, we have a TensorFlow invocation overhead. So each time we want to have a prediction, we're going to have to invoke the TensorFlow. We have to invoke our model. This goes through a Python code, then this is interpreted in some other codes. So we have this type of overhead. Now, the prediction performance was not that good neither. Why is that? Because the neural networks, they were good to approximate cumulative distribution function shapes, but they did not perform well on single data instances. Okay, this is what they call the last Maya problem in the paper. But I'm going to show you an illustration of that in the next slide. And as I said before, B trees, they are cache efficient, they are optimized, but neural nets are not that well optimized for this type of lookups. So you see that clearly your constraint is going to be speed and performance, right? So as I said, this is the illustration of the last Maya problem. So here the neural network is really good in approximating this cumulative distribution function between the key and the position. But if we zoom in, here we see what actually happens, that we have gaps in our curve. And this is basically the problem they are facing to learn B trees. Now, the solution they used is they came up with what they call the learning index framework. And they layer models with a recursive regression model. So what happens here basically is they're not going to train one model for the full key space anymore, but kind of expert models, right? So what you see, this is not a tree, but what happens here is you want to illustrate that you input the key to model 1.1, and they're going to tell you, well, for this key you should interrogate model 2.1, and so on and so forth. So this will help you basically to narrow down the error rate, because you have an expert model for each of each slice of your key space. Now, this is what they call a recursive model index. The output of this model is basically a page. And the other optimization the authors do is now within this page, instead of performing binary search, basically they propose the biased quaternary search. This is basically like binary search, just with 3 pivots. and they're going to interrogate 4 slices in same time. So it's always between the position minus a sigma and plus a sigma. And this basically, the sigma is the min error and the max error that I talked before about earlier. All right, so to evaluate this trained model, they compared it to a very good implementation of a B-tree on a data set of maps, so with 200 million features, or I should have put records here, because I got the machine learning and database terminology a bit mixed up. And so basically here we see the results. We have different page sizes, so they evaluated the page sizes, but also the stage size. So basically this means how much key space does one stage cover, okay? So, and the results, they're quite impressive. So we can see they also compared binary with quaternary search. So I'm not going into all the details here. You can look in the paper for yourself. But basically the bottom line here is that the model basically dominates the B-tree structure. So it's up to 3 times faster, and it requires significantly less storage. So if I look at the B-tree, the smallest B-tree here is at 6.5 megabytes, whereas the largest model is at 3 megabytes. So it decreases the index size by half. Right? This is quite an achievement. On another evaluation, they used web server logs of a major American university homepage. And so here maybe I should have said, here they indexed longitude information. So it was a fixed sized long value. Now here they indexed timestamps. Okay, so here again, basically same results. We see a big increase in speed and a lot of saved storage space. All right. So again, it dominates the B-tree. So now, what about the hash tables? Right. So if we use this this new model, so this recursive model index to learn this cumulative distribution function, we can, that's what the authors say, we can obtain better hash functions. So what they try to optimize here is basically the amount of empty buckets. So they want to have less empty buckets. And they achieved to do that. So if we look at so here we have the map data, the log data. Well, I didn't talk about this last data set before. This was generated data, so I thought it's less interesting. Now, here we can see that the model hash has a much lower amount of empty buckets. So 0.5 versus 25. So I leave it to you to check the results in details. So, and again, with less empty buckets, the storage space is optimized a lot, right? So the same holds true for Bloom filters. Now here, the analogy is a little bit different, right? Here, the Bloom filter is a classifier returning a probability of an element being in the set. Now, remember I told you that with a Bloom filter you can have false positives, but never false negatives. This is something the machine learning model cannot guarantee. So, what's the solution for that? The solution the authors propose is that they build a Bloom filter, but only for the false positives of their trained Bloom filter model. Okay, so that means when they tell you, okay, the key is in the set, and your probability is not high enough, you can always go look up if this is in the false positive set, yes or no. Okay? And then you can have the same certitude than with a standard Bloom filter. So here again, they made an experiment. So, but this time. This was done with blacklisted URLs, blacklisted URL data set, and basically we see again that the memory footprint drastically lowers, but at the cost of a false positive rate that increases. All right, so basically this is it, what I have to say from the paper. So I remind you that in the paper you have a lot of more content, so it's a 30-page paper. They are really detailed in the appendix with all the mathematical cost functions they try to optimize and to run it. Now, maybe a few words. I chose this paper because I found it was really exciting how machine learning basically can mimic algorithms that have been developed over a long period of time and achieve to obtain better results. Well, of course, this has to be this type of research has to be extended to automate it even further. But I think this is quite interesting how machine learning basically can mimic algorithms just by looking at an input and an output. So now maybe it's your turn. So what do you think? What are your thoughts about what I just presented to you?
So I like it because now you can see how can you scale this, because an algorithm, you do such a work, to build for FAT, for NTFS, different type of algorithms, and now you use machine learning, and you have better, from our point of view, you have better, speed, better structure.
So basically, you're saying that what you like, basically the same than I do. You have those algorithms basically that have very evaluated.
Working, to optimize everything. I remember in the history of first PAT, and you have NTFS, and all these types of structure the hardware, and compromise and take a look at speed and all this stuff.
Yes.
You have machine learning, and then you beat every algorithm.
Yes, I agree. Yes, please.
I think it's pretty interesting, like especially during the performance improvements that you have. Though I'm wondering if how does this work in live systems? I mean, that you have like a bunch of data that you want to index. You build your index system, which is super fast. But for example, if you take if what you have is a data warehouse, that's perfectly fine. You will query your data and you will be happy. But if what you have is kind of like a live database system, it means that maybe in 2 months the data that you are supposed to index will be completely different. So it will mean that either you will need to have online changing index, like your models will change, or that they need to provide robust enough indexes for it to be long-lasting in terms of that.
So you're basically saying you're curious to see how this is going to evolve when the model has to be retrained, right? So basically to serve a high workload when you have a lot of inserts or deletes or whatever, how can your model be adapted? Is it going to be fast, or how are you going to do this? This is what you're interested in.
Do you have any performance figure about how long does it take to train the indexes?
I don't know by heart, but it's written in the paper. I think it was a few seconds actually.
Okay.
Yeah.
How long does it take to retrieve, to find elements?
So the question was how long it takes to retrieve the elements. So here this is basically in the results section. So here, so I'm looking for the best performance. Wait a second. So the fastest in search was 82 nanoseconds. For the model, okay, versus 265 nanoseconds for the B tree. Yeah. So it's quite impressive, right? Okay. Are there any more comments, or should we move on to the? Yes, please. Okay, so the question was in what case we use this type of Bloom filter. So I'm just going back to to the slide. So here, this is the storage. Okay, I'm going to take it back off. Basically, Cassandra, RocksDB, or LevelDB. Okay, those are key value stores. So for a certain key, you can retrieve a value. All right. Now, on the disk, those keys, they are stored, or the data is stored in different files, as you can see here. Okay, with each level, you have more files. Okay. So now, when you're going to fetch a key, you don't want to seek through the entire file. Okay, so you just load the Bloom filter, and you ask, is my key in that file? And if it says maybe, you can look for it. But if it says no, you are sure it's not in that file. Welcome. Okay, so move on to our last speaker, that one.
So I'm Redwan, and I will present the paper Play in Atari with Deep Reinforcement Learning, written by DeepMind. So I will cover those points. First, we'll talk about reinforcement learning and the difference between supervised, unsupervised, and reinforcement learning, and the mathematical modeling of reinforcement learning. Then I will talk about Q-learning, which is an algorithm for to solve reinforcement learning problems. And then I'll talk about deep Q-learning, and after that deep Q network, which is the contribution of this paper, and then finally a discussion. So what is supervised learning? So as you know, in supervised learning is a type of problem where you have a pair of data, x and y, and you want to find the mapping between the inputs and the outputs, your x and your y. So we would like to find or to estimate the function f such that y is equal to f of x. So, and we use f to map the new examples. So the typical examples of supervised learning is regression and classification. So in unsupervised learning, we don't have labels, we don't have feedback, and we try to find hidden structure in the data. So typical example of this is clustering, where we have a population and we'd like to find groups in this population that has similar characteristics. So reinforcement learning is a different setup. So in reinforcement learning, we have an agent and we have an environment, and the environment gives to the agent the state or the observation, and the agent tries to make the best or take an action, and finally the environment gives back the reward and the next state. So the objective of the reinforcement learning is to maximize the expected reward, future reward, the accumulated expected future reward. So typical application of reinforcement learning are games. So the first one is Atari game. So here the state is the screen, is what we see, and the action is whether it's to move right or left. So and the reward is we'd like to maximize our score after finishing the game. The second example is Go, which had a huge success with reinforcement learning. So the state here is the position of each of the pieces, and the action is the next place of the new piece, and the objective is to win the game, right? So what is the mathematical modeling of reinforcement learning? So in reinforcement learning, we model the problem in reinforcement learning as a Markov decision process, which consists of a state space which contains all the state or possible states in that the environment can be in, the action space which contains all actions possible that the agent can take, and the transition probability matrix, which contains the probability to go from a state to another state, given that we take an action A. And reward matrix, which is the expected reward of being in state S and taking action A. So this is a stochastic reward. So it's another definition is, so we can define the policy pi is a mapping function between the state space and the action space, where this function tells us what action to take if you are in state S. So the objective now is to maximize the cumulative expected reward, which is written in this equation with a parameter gamma, which valorizes the near future reward compared to the far future reward. Okay, so here is a typical, or it's an example of optimal policy, which is, here it's the grid word. So the state is the cell, the position where we are, and the action is whether to move right, left, down, up, and the objective is to reach the end states. So the optimal, here I'm showing the optimal policy for this kind of problem. So for each cell, you have the optimal action that you have to take. The red path, the green path, sorry, is the special case of the optimal actions when the initial state is the first cell in the corner. So how we can find the optimal policy? So in order to define how to do that, I have to give you a definition of Q-value function, which tells us how good it is to be in state S and take action A. So with respect to some policy. So it is the expected reward of the expected reward that we will have if we apply action A in state S, and then we apply policy P after that. So the optimal the optimal Q function of this Q star is the optimal expected reward that we can have if we are in state S and we take action A. So basically, we maximize the expected reward with respect to every policy after we take the action A. So So how we can solve this? How we can find this Q star, which we want to do. So there is a Bellman equation that tells us how to find Q star with respect to S and A. So basically, it's shown in equation 4. So the idea here is that the optimal Q star that you can have is what you will get as a reward after applying action A, and the maximum, or the Q star, the maximum of that you can have in the next state S prime. So that's why we maximize. That's why we maximize the Q star here with respect to A prime to the next action in the next states S prime. So what is the algorithm to solve this, to find the Q star is called the value iteration algorithm, or Q-learning algorithm, which iteratively updates Q star in each time slot. So, for example, in time slot t plus 1, the q star of s and I is equal to the expectation of the reward that we had plus the maximum of q star in time t of the next state and next action. So the drawbacks of this algorithm is not scalable because we need to calculate or to compute the q function for every state and action pairs, s and a, and while in real life problems we have like huge action space and huge state space. So this is not scalable at all. So for the solution of this, we use a function of approximation to approximate the q star with machine learning algorithm. So when talking about deep Q learning, so we use neural network to approximate this function. So we use the neural network with weight w to approximate this function, q star, and we use the loss function L, which is the difference between our objective and the current q star of time t. And after that, we use stochastic gradient descent to optimize the objective function. And drawbacks of this algorithm is that your samples are not IID because your current states, when you take an action, so the next state depend on the action that you take in the current state. So your IID your samples are not IID. So how DeepMind solved this problem is by using what we call the experience replay. Is that we store each transition in a replay memory, and to train the network, we use mini batch or random mini batch samples of this replay memory, of these transitions in the replay memory, so that we can break down the correlation in our samples. So the algorithm proposed by DeepMind is, in the beginning, we initialize our replay memory to a capacity n. We initialize our weights, and for each episode, which is the game here, we initialize our initial states, and for each time slot, we take an action with probability epsilon, and here we use the epsilon greedy policy, which is in reinforcement learning we have to make a trade-off between exploration and exploitation. We need to explore the new action that we didn't see in the past, and at the same time we need to exploit what we have learned so far. So we need to do epsilon greedy policies to select new actions with a probability epsilon, and to use what we learned so far with a probability 1 minus epsilon. So we take the action, we execute the action, and we receive the reward and the new states. And after that, we store this transition in the replay memory, and we perform the gradient descent to optimize the weights of our networks. So here is a result of this DeepQ network. Is a video published by DeepMind for playing an Atari game. So here the input is just the raw pixels, and the action is to move right or left. Okay, so this is 10 minutes of training. So as you can see, the agent doesn't play well. But after that, we can see that after 2 hours of training, it plays like an expert. Yeah, great job. Now, after 4 hours of training, it's figured out that the best policy is to create a tunnel near the wall there. As you can see, yeah. So, to summarize, very quick. If you combine Q-learning with neural network, you can achieve superhuman performance in several Atari games. Well, second thing is that a single model can play different games without tuning the model for each game. But the problem in reinforcement learning that we can't find really other application where we have a huge success except games. The reason here is that in games we can generate experience as much as we can, as much as we want. Right? So in real life problem it's not the same case. So the conversion rate is really a big issue to tackle in reinforcement learning today. Other challenge is the reward function, because we need to define the reward function in order to apply reinforcement learning. But some application or some problems, we don't know what is the reward function, and with design of this reinforcement reward function become very difficult. So we're trying to find out some ways for the agent to learn the reward function by itself. Yeah, so thank you for attention and any question.
I have a question.
Yeah.
Do you know why they use the square regulation on the last algorithm, when you go back in the algorithm? Have you tried to implement this, or?
No, I didn't. This one?
Yeah.
Square error? Yeah, this is typical loss function that we use in the neural network. But why do they use it?
No, to try to use other type of.
Because this is a regression problem. So regression problem, this type of loss function works very well. I don't know what kind of loss function you think it will be better here.
No, just to try, to see if you have more speed, or to see what is happening.
Okay, no, this is the main loss function that they used.
Yeah, you come near with square, but
exactly.
it depends on the use case
okay.
of the game or something like
But
that.
in regression problems, I guess this is the best loss function that you can do. I think.
Sometimes L1 works also.
Yeah,
L1.
the same.
Mm-hmm.
It depends on use case, I think.
Okay. Okay. Any question? Okay, thank you.
So then, thank you again for coming. I also want to thank our sponsors, which are the SNT here and Amazon Web Services. And I also want to thank the viewers that watch this meetup on YouTube, and hopefully we see you next time. Okay? Thank you.
When will be the next?
Sometime in June. We have. I also want to, if you're interested in giving a talk, please make propositions. We have a Slack channel also. Franz, how do we connect to them?
The channel is available here on www.datascience.lu, and there is a Slack logo somewhere, and if you click on it, it should work.
Yes, and there you can make talk suggestions, and also if you wish to be speaker, then we can probably arrange that. Okay?
You can also reach us, like right now, there's Eric,
yes.
Chris, and me, and yeah, if you want to have a little chat, that's definitely the moment.
Okay. So what would be interesting from my point of view, and maybe you will have more attraction, maybe if you have, if papers and maybe some use cases where the papers are used, for the people that are not so techy, so
Yeah.
to read one of the papers.
Well, this basically papers, the papers that we love, this was a kind of thing that we wanted to try. So usually we have something more applied people talking about their work or how they use data science and machine learning to solve a concrete problem. But this, we thought it's kind of nice also to see what type of, or kind of like vision talks, what is happening, what is...
But you know, some people here, I think that they need more, more this, because you have more correlation between, you know, use cases.
Yeah.
It's much easier to understand maybe some concepts.
Okay.
Because I think it's about concepts. For some people want to go deep.
Okay.
You know, just you know how is your community. I'm first time here, but
No.
it's very interesting and very clever.
Yes, indeed. The use cases they...
I appreciate it.
So then, thanks again, and like I said, see you next time.
Artificial intelligence podcast several weeks ago, the concept we spoke about. This is where you got an idea. Sorry for you.
No, that's fine. That's fine. What's the definitely? I think it's